Hello, it's David, and welcome back to my Atari Falcon motherboard restoration series. This is the board here with no CPU, and we saw at the end of last episode, which I'll link it up here, that when we injected power into the board, nothing blew up, nothing got hot. It drew roughly the right amount of power, but obviously we didn't see anything on the output because there's no CPU. So the next step is to figure out what we can do about the CPU. Now, if you haven't seen that video before, you can skip it. It's not required, I hope, for this one. It's quite long, it's quite tedious, but it does show the process that I went through to get here. And if you're trying to do something yourself, that may be of interest as reference. If it all goes wrong here, then take it as what not to do. But there it is, if you would like to see it, linked up above. So the plan is to use an accelerator card. This is my DFB1 open source Falcon accelerator card that I have built on the channel, and again there'll be a link somewhere up here for a playlist on that. And my plan is to use this to substitute for the CPU, because that's kind of what it does, except that we will have to do some modified firmware because it assumes that there is a CPU on board. This is one of my development cards. This is the DFB1 R4. Revision 4, so this was the actual release version was revision 5. So this version still has a few bodge wires on it, but I believe the firmware is otherwise pretty much the same. I've installed it in my working Falcon here, and I've jumped it such that it's using the onboard ROM, and it's running at the system speed, which is 16 megahertz, and it is clocking at 100% on the integer division score, which means that yes, it is running at 16 megahertz. Fair amount of hacking later, and what I've got now is the red LED. This is still in my working Falcon. I've got my the red LED here to indicate whether bus grant acknowledges high, i.e. am I bus master. The orange here, which is, that's drowning it out, isn't it? The orange there, D2, that's indicating bus activity, so the address strobe going low. The green one there, which is pretty solidly on, that's ROM activity. And the blue one blinking there is an indication of the clock. So that's every, I don't know, whatever, 800,000 pulses or something like that. That'll oscillate, and it basically gives an indication of the clock speed. So if I switch into 8 megahertz mode, which I've tested, that halves the frequency. So that's roughly what it looks like. If I hold reset, you see that's the reset line goes high, and there you go. You can see that's gone into 8 megahertz mode, and there's no other activity. When I release, you can see, there we go, look, the AS lights and dims, and that jumps up to 16 pretty much straight away. So I've got a little bit of just basic diagnostics in there. Now, what I have to do is to completely rip out the bus arbitration logic in here and effectively pass that straight through from the CPU. So, right, well, that's the next step. And then it'll be bye-bye to this board, because once I've done this, it will not run in my proper Falcon build anymore, and we will be completely on to the board under test. Allow me to commend to you the sponsor of this video, PCBWay. Now, as the name suggests, they are a PCB manufacturing company, but they also do PCB assembly, PCB design consultancy, sheet metal fabrication, CNC machining, 3D printing, and they have an extensive library of shared projects contributed by their users. There's also a module store where whole items can be purchased pre-made. If you think any of these maker-centric services could be of interest to you, please do have a look at their website. I thank them very much for supporting my work. This is the concoction I've come up with. This is the bus grant out pin, which is not connected on this board. So I've just used one of the spare pins to drive that, and I've written a firmware that basically connects the bus arbitration signals through. Obviously that doesn't work on my main Falcon board, but I can see the LEDs doing their job. So here we go. We're going to have a go at getting this connected in here. Maybe I should put a bit of contact cleaner in there, actually. I think this board has always had a little bit of a history of being a bit susceptible to poor contact. And yeah, the fact that this one down here is shorter Still is a bit of a surprise to me. It does kind of sit at an angle. I wonder if that was intentional, because that's obviously where the keyboard would go. Okay, I can't get the whole board and the power supply and everything else in shot, so here's the DFP one, and I've got the meter here just to do a bit of a voltage reading if we don't see anything. And right, we're set to, I've increased this again 2.5 amps because this is a bigger power draw in here now, and we've got a what's it called, a voltage regulator in here and a few other things. So I've increased it 2.5 amps, 5.1 volts again, and here we go. Going to press my button, output on. Oh, we got a brief flash. Something happened. Let's press reset. Reset's being detected. Don't see a clock. Should be seeing a flashing blue clock. Let's just do some testing of the voltages. So that should be 3.3 from the regulator. Yep. And I think that should be 5. Okay, well that's good. But no clock. Power off. It's showing 1.9 amps. Pardon me. I think we need to get the scope out. Okay, sorry about the background noise. The oscilloscope's now on. I'm afraid this is going to be a little bit tricky to probe because or to film, because I'm struggling to get both in shot again. I've just got nowhere for the camera to go, so I'm kind of like looking through the camera arm at the moment. So yeah, sorry about that. We'll just have to live with it. So we're connected to ground over here, and the first thing I'm going to do is going to start probing that. That's the X CPU clock. That's actually what should be generating. Well, that should be providing the 8 megahertz, and we're not seeing that flash. So let's do that first. I'm putting the power back on. There we go. We got our reset flash. Some activity going on here. There we go. Okay, yeah, that doesn't look right, does it? All right, power off. So I think we better take this board out and actually probe the clock patch that I have undone. Perhaps that was not such a good repair. Okay, what have I got coming out of here? Nothing. There's no clock. Well, that's... oh dear. Okay, so that is... sorry, you had a shot there, aren't you? Bring you down here. So I was probing the top side of R217 there, which should come straight from the COM bell, and that is producing nothing. And obviously, well, none of the downstream clocks are therefore producing anything either. That's that top side of 217. That should be at 8 megahertz. Oh dear. Top side of R217 there is supposed to be connected to the COM bell pin 191. So let's have a look. There's 190 flagged. So it should be the next one along. So it's definitely connected. Following the chain, R234 is the next place. There we go. Where the clock comes from. Okay, so that's that via there. Going to R234, which is a 22 ohm resistor. Following the trail then, after R234, we end up at link 102, which is fair enough. I don't know if that's an inductor or just a 0 ohm resistor. And then from there we go to Q7, which seems to have a connection. But looking at that, that looks to me as if it doesn't look like the solder's very good there. But that looks a bit pitted. Now, given that U65 seems to have had some work done, I fancy, and this is bent over as well, I fancy that that has had some work done. So what did I do? I flipped over the board. Now this is very reflective, so it may not make for a good picture on the video, but that is the backside of Q7. Now I'm going to hazard a guess that that's been removed and reinserted. And I don't know about you, but that pin there does not look like it has much in common with that trace there. I need to just move it over a little bit more. There we go. Reflow that in there. And get this one soldered into place here, and then just trim off that 90-degree turn. Decent blob there, it's got flux inside it. I hope that that has now given us the VCC connection to the top of our 252 there. So scope on the screen, power connector back on, let's throw the switch. That's the wrong switch. Try that again. There we go, we're getting a signal of sorts. And we are, well, that's an average trigger level 3.2, and we've got a peak to peak of 2 volts. That's pretty poor, but hopefully that is now producing some output. There we go. 8 megahertz. Perfect. Okay, so brought back in my DFE1R4, and we're going to keep our eye open now for the pulsing clock signal on here. Here we go. Power's coming on now. There we go. We've got a pulsing clock. With the clock working, then it's time to start probing around, and well, I've actually run into a problem already. So let me just show you what I've got here. I've got one oscilloscope probe. This is channel 1 on the AS line, that's your address strobe, and one on the UDS line, which is generated by my CPLD. And when I power on, watch the scope here. So we've got a yellow line, which is address strobe, and a blue line, which is UDS, and we'll power on quickly. There we go. And you can see pulsing away here, no activity, and it's all gone high. If I reset that, oh, I've just lost my ground. Hold on, let's turn that off again. Okay, power's back on, flashing. If I reset, there we go. We are actually getting a signal, but in fact, there's the problem. Let's turn that off and power down because I don't want to damage things. What do we got here? We have, right, so we have the both channels, so the address strobe and the upper data strobe come along here, and then that's the first activation, and they both go active at the same time, which is pretty much what you'd expect from an 030 during a read operation. Something obviously terminates it. I'm not tracking DTAC, but I presume there's a DTAC in there, because that is, what's that? That is about 400 nanoseconds, which is quite long actually. But this is running in 8 megahertz mode, so one cycle is 125, so you 250, so it's 4 cycles. Yeah, no, that's a bit long, but anyway, let's not worry about that for now. That's terminated. Then it's off for a second, and a second assertion, and you can see that the address strobe, the yellow line, goes low as expected, but we have an odd looking UDS line, and if I not position, let's use the trigger there, right? So if I use the trigger to give me a voltage, 1.6 volts. Now what that says to me is contention. I, as in the CPLD, am trying to drive that signal low like I did previously. Something else must be driving that high in order to get 1.6. It's not shorted somewhere because we had a low signal before, so something's driving that high, and I think I know what's going on. I think I've made a bit of an oversight here in this firmware that I've done. UDS and LDS, the upper and lower data strobe, do not exist on the 030. They have to be synthesized by the CPLD. The Falcon is an 030 board, so they don't really exist on the Falcon board either. It's a bizarre bastardization of the interface that Atari have done here for the expansion port, where it kind of looks like a 68,000 interface with UDS, LDS, and no A0 line, but the actual board itself has A0 and size lines, and so it's all actually translated by these GELs here. Now, specifically, UDS and LDS are synthesized by U62, which is this top one here, and I'll wager if I pull that chip, we will see that work. But I think there's more to it than that. Basically, something amongst these chips decides that this is not going to synthesize. It's going to start listening and translate back to the size parameters and address 0. Basically, these sort of switch the direction they control whether the expansion port over here is a bus master or bus slave. And the way they do that is through U68 here. Now, the equations to U68 have been, I don't know if they've been published or whether they're reverse engineered, but I'll put an overlay in here. I'm looking at these, and they have a basically they have an equation for the high Z line, and when the high Z line is active, basically these switch operation, they translate the signals that my card is sending into one suitable for the motherboard. Otherwise, they are sending the signals from the motherboard back to my card, and that's what's going wrong with this contention over here. I'm pretty certain of that. So we need to basically trigger this reversal. Now, the way that we do it with DFB1, the normal DFB1, that is that the CPLD here basically negotiates with the underlying CPU, the one that's missing on this board and hidden under here, but basically to take over bus mastery. So it actually halts both processors, then it makes a bus request which the onboard CPU grants, then this one tells this one it can unhalt, and it basically releases the bus hold on this, and it starts processing. When something else, such as the DMA, which is over to the right here, or the MFB, wants to interrupt processing, not the MFB, sorry, the under here, COMBEL, which has the blitter in it. When that wants to interrupt processing and gain bus mastery, it makes a bus request. And my CPLD passes this both to my processor and then also onto the onboard processor, so that they both release bus ownership and allow that to happen, allow the DMA cycles to occur. And then it goes through the same process of requesting bus mastery from the onboard processor whilst keeping it halted. Now, obviously, I've undone most of that work in order to get around the fact that there's no processor on board. But how do these GALs know when to basically go into this bus mastery mode? Looking at the equations, I think it comes from the bus grant line on the from the processor underneath. Now, the problem is that there's no processor to issue that bus grant. So what I've come to realise is that, quite the contrary to what I said earlier on about having the missing CPU, meaning that I can just wire things straight through and it's a lot simpler, I obviously have to trick these GELs into letting me speak to the bus in the same way that I do when there is a CPU present. So the simplest thing to do is to actually tie this pin here. This is pin 4 on U68. This is the BG030, so it's the bus grant signal from the unpopulated 030, just wires straight to there. If I tie that to ground, then basically I can revert to the original firmware, potentially even just put a normal DFB1 in here, and it will go through the dance of getting of doing the bus arbitration and getting the signal. So I think I can either tie it directly to the bus request, so that every time bus request goes low, it's granted, or just I think I can just tie it to ground. So what I might do is just run a resistor there to, which one is ground? I think that's ground, isn't it? So just run a resistor underneath, maybe something 1K, because I think that's just floating at the moment. And I'm going to revert the firmware on my DFB1R4, test it in the other board to make sure that it still runs, and then we're going to have another go. Well, sorry, I forgot to press record, but there we go. That's actually a 10K resistor. I just happen to have it lying on the top of my pile. Like I say, I think that's floating, that line, so with no CPU present. So any kind of resistor pulling it down to ground should give us an active low signal, so that's absolutely fine. And there we go. We'll just plonk a little bit of Captain tape over that to keep everything nice and contained. And there's a quick confirmation that pin 4, which is the bus Grant 030 line, that's coming from the shield there, that reads 10k to ground. Right, so here's the current test setup. This is the DFB1R4. I have reflashed it to re-enable the bus arbitration, and I've tested it on my other Falcon to make sure that it boots up. We've got it configured in, actually there's some disable mode, I was just experimenting with that. So we've got it configured to not use flash and to run at 16 megahertz, so it should be using the onboard ROM if one exists. I've got the test cartridge in here, and we've got a probe here on the AS line, which I can get there on screen. I've also got the back here. I've got the monitor connection in. That's this black one just on the edge of the screen here, and I've also got an RS232 there. Outputs on. We've got a flashing light. We have no activity there. We're pulling 2 amps. Let's hit reset. Okay, I'm not seeing anything. Let's power that off. Right, so I'm getting a low on that bus Grant, so that's good. Oh! We're getting some execution. In fact, we're getting sustained execution. You can see the orange light there. That indicates AS is toggling. It's on the screen. Okay, so we've got something that needs a few resets. Nothing. Okay, so nothing on my VGA monitor. Let me have a look and see if I've got anything on the serial output. No, just some gibberish as the power came on, I think. So it doesn't look like we're successfully executing the cartridge. These 4 links over here going to the cartridge port, I think this is like LDS, UDS, ROM 3, ROM 2 or something like that. So one of these, well basically UDS and LDS. There they are. That's toggling away nicely. Matching AS. And you can see that's at the 3.3 volt. I haven't got it on there, have I? Measure voltage, Vmax. There you go. So that's at 3.5 volts. So you can tell that's being generated by my CPLD. Measure, you can see that's higher, so I think that's channel 2 voltage Vmax. There we go. Yeah, there we go. 5.68 maximum there. So that one I think is the ROM select signal. So I think it is actually executing code from the, and nothing on there. So that's probably the ROM 2. I think ROM 3 is the lower range. So that is, I think that's executing code from the cartridge. Well, there we go. Okay, but we've got nothing on the screen and we've got nothing on the serial, but this is a start. Okay, let's have a think. There's absolutely nothing in the board that can't be removed, or that can be removed, sorry. So it's as good as time as any to test this. This is the DE, the display enabled pin on the Videl, and is a good sign of a broken Videl if it's not working. But there we go, we've got some signal pulsing away there, frequency 16.6 kilohertz. So I think that's a good sign. I was doing some probing off camera, looking at this reset circuit. So this is the 555 chip here. And this feeds into U11 down here, and that's what inverts the signal. This, I believe, is open collector. So this inverts the signal and pulls reset and halt low when the timer is activated. So I was probing around here to try and figure out what was going on with these reset pulses we were seeing. And basically what it boils down to, and I've tried to do a little bit of a circuit simulation to confirm this, is that C1 and C7, which is this one I believe, are in the reset circuit. Not quite sure what C7 does, other than to put a bit of undue strain on the on the sort of dual inverters, not gates, going from the switch into the 555. But C1 here is the main one that controls the timing. And basically, when the switch is pressed, this gets emptied. This then slowly refills over time, and once that gets past a certain critical voltage, the 555 kicks in and drives its output high, gets inverted by U11 and passed through to reset and halt. Therefore, if this is a short push on the reset button here, C1 doesn't charge quickly enough, and the circuit waits in that reset state until that passes the critical threshold, and then we release it. Sorry, I think I said that the other way around. This has to be high in order to release the signal. The moment the button's pushed, the signal is asserted. So this basically ensures a minimum reset period of around 300 to 400 milliseconds, depending on exactly the condition of the caps. Well, or specifically that cap. That's in good condition, measured it, and it's charging fine. So what we were seeing was when the button is pressed longer than that, about 300 milliseconds, C1 here reaches its threshold, and effectively any noise on this switch, bounce or anything like that, that is long enough to overcome the two NOT gates going into the 555 circuit, gets passed directly through onto the output for U11 and therefore onto the reset and halt pins. So that's what we're seeing. So I think that's a red herring. I don't think that is it's a problem, but I don't think it's actually what's stopping the machine booting. So the trick is, I think, short presses, keep it under that 300 milliseconds, and then this cap can do its job and we'll get a nice clean reset signal. So I moved on from that and started looking at other things. All these gals here are actually from my working Falcon. I removed them from here, put them in my working Falcon to test, and they were fine. So actually I just put my working Falcon's ones back in here. So these gals tested out okay, as did U44 over on the other side of the board there for the DSP. That's that one there. I did try with and without the codec chip. No real difference to anything that I could see in my reset probing, so I've put that back in because I haven't changed those half moons that we saw over on the other side of the board. So during all that probing I was doing of the reset circuit here, I had my diagnostic cartridge and the serial port in, and I was just flicking away at reset happily, and suddenly I got this on the screen. I actually didn't see it in real time. I scrolled back and there it was. So clearly something had started running. A few more taps of the reset button later on and I could reproduce it. And what we're seeing here is basically a list of memory address errors, or not memory address errors, but memory line errors, data line errors. So this is testing address number 8, and it's writing zeros mostly, I think, to it, and then reading them back, and nothing should be 1. There's a lot of 1s. So fine, perhaps we have a problem over here with the memory board. I did the same thing I did with the gals. I took this board out and I put it in my working Falcon, and actually it passed all memory tests. So that's good. I thought this was a bit dodgy, but it seems to be okay at the minute. Reverse the procedure, took my memory board out of my Falcon, working Falcon, put it in here. Couldn't see any difference. But carried on probing around, trying a few different combinations, and moved on to manipulating the board. What I was thinking is perhaps there was a bad connection. I tested all of the row address and column address lines, which are down here on this memory board, and again couldn't see anything obvious there. They were pulsing away. I didn't capture all of this, I'm afraid. It was fairly dull, but I couldn't see anything wrong with those. Nothing strikingly obvious anyway. And so I moved on to sort of like tapping chips and flexing the board a bit. I was thinking maybe, you see down in this corner here, this is where the data lines are. Under this probe, this is the data lines from my DFP1. I was thinking maybe there's a bad connection here, so I applied contact cleaner, and I've sort of just been flexing the board around in case there's a problem. And then that's when, well, this happened. This is actually producing proper RGB output. I had done a bit of probing and noticed that one of the W10, there's a there's a jumper here at W10 up by the in the modulator area, and that pin, the non-connected pin at W10, is the H-sync. So I was probing that and noticed that I was getting a PAL refresh rate, like 15.5 kilohertz, rather than the 30 something that you'd expect for VGA. So I actually switched over to my RGB monitor, and so this is where we come in today. So this is appearing on the serial line as well, I should say, but this is obviously much nicer here. I'm going to have a go now, just flicking the reset button. There we go, less than 1/3 of a second. Is it reproducible? It is. Now I should say that this error actually is on an address FF8936, which is part of the SDMA chip over here. So if we can get this to reliably reproduce, that will be the subject of our attention. But what I'm interested in at the moment is actually what happens if I start manipulating the board a bit. So I've got some probes on here at the minute, but I'm reluctant to take them off. You see we get the same error message there, FF8396. But what if I sort of just pick up one corner of the board? No, that's good. And the other corner? The same. What I'm looking for, you see, is a pattern of behavior which would imply perhaps a damaged connection or a slightly cracked trace, and where you flex the sort of the board like this, you can either push, if it's on the top, a broken trace, you can push it together, or if you flex it like this, you can pull it apart, and just helps you sort of localize a problem that's going on. So I'm just going to hold the board from one corner. No, so this is really promising. The fact that I can reproduce it so many times. I'm just going to put power off, let it cool down, and put it back on. Same again. No, this is quite promising. Right, so I think what I'll do is just going to disconnect these probes. So I was looking at the reset line and the cartridge ROM activation line whilst probing my resets there. But we actually want to be having a look at the SDMA in a moment. I'm just going to try, actually with the probes off, let's just try that again, make sure that it's still behaving. Yeah, FF8936. That's put in 2.3 amps now. And I'm just going to try reseating DFP1. Just going to give it a bit of a wobble, should still be connected. See if that has any effect. Right, there we go. You see now, there we are. That suggests, and we don't have the yellow light here, that suggests to me that perhaps there is still a bit of a problem underneath here, or maybe it is just dirty contacts. DFP1 we have seen works on my other Falcon, so that would tend to imply, I've just reseated it back down, yeah, nothing going on. Look at that. Just a little bit of movement. So that would tend to imply that the card is probably okay, but maybe there's something wrong with these pins on the motherboard. Just another little bit of a wiggle. There we go, look at that. This is how delicate this is. No. Okay, so let's have DFP1 out. My suspicion falls immediately to this bottom connector down here, purely on the basis that that's where all the data lines are, which seem the most likely to be causing a problem like this. I suppose it could be the address lines, but when we did get that cartridge memory test working, it was highlighting all sorts of errors. None of these are loose. But the other thing was that this, if you recall, these lower connectors were a different type to these upper ones. I can't see any evidence that they've been reworked, but perhaps they're just not making a very good contact because the board is sort of having to sit at a bit of an angle. Yep, clunk. That's a good positive clunk. Right. We'll try again. Power on. Okay, that's interesting. It's actually crashed halfway through refreshing that screen. Give it a reset. Now that could be actually, I suppose it could be the reset circuit, but there we go. So I think potentially our initial issues were mostly centered around this this connector over here. The fact that we can, by cleaning and reseating, we can kind of reliably get, well, I mean, obviously code's executing. This is brilliant. This is actually, this is nearly a working motherboard. So this is the SDMA chip, and I've had a quick look on the schematic, and I can't see an obvious chip select signal. In fact, the entire 23 line address bus, 22 line address bus, there's no A0, is there? Actually attaches to this chip. Most of the pins between 3 and 31, so all on this side, are actually the address bus. So it's possible that it self-decodes, that it knows that it's being addressed. I'm not 100% sure, but that had me thinking, if it is self-decoding and it's looking all along these address pins, could we be having a problem here? Now, I'll be first to admit that the techno shed here is not the most spick and span place in the world, but that does not look like the best cleaning job I've ever done along there. Is there any little hint of a problem around this area? Not 100% sure, but I think my first port of call might be to give this a bloody good scrubbing with the old toothbrush and the contact cleaner, and see whether we can improve the situation along here at all. Toothbrush and hairspray, plastic grin, Miss Grey on the corner has just walked in. Bum, 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 bum. Well, cleanliness is next to godliness, they say. I'm not a religious kind of a chap, so I won't be doing any praying, but let's throw the switch and see if that's made any effect. Oh, different error. Oh, initializing keyboard. Wait. I covered that up with the cutout. We've got a blue screen. I don't have a keyboard in. We've got a blue screen. Let's let me get a keyboard. So the keyboard connector is under here, and it's not in a great place. The keyboard cable is not very long, so I've popped some cardboard underneath there to try and insulate the bottom of the keyboard, which does have conductors and chips and bits and bobs on it. Yeah, not the greatest setup. Okay, so power coming back on again now. I've got a green light on the keyboard. Checking if bus. Oh no, we're back to the. Oh, the DMA's failed again. Oh, that was short-lived. I wonder whether it needed pressure on it, or perhaps it needs reflowing. FF8396. It's the same address, I think, isn't it? Oh, what a shame. Okay, I've taken the keyboard back out, and I'm just going to give that another quick brush. Dry this time. Still worried about that little section there. It looks a bit odd to me. Let's just try that. Here we go. Power on again. Okay, let's try applying a little bit of pressure. I'm just going to swing the camera that way a bit so you can see what's going on. And I'm going to apply downward pressure onto the chip and hit reset. Blue screen. Release the downward pressure. Okay. Maybe it is time for a little bit of a reflow along here. Just before we get the soldering iron out, just having a little inspection around the SDMA chip here, coming at it from the other angle. I can't see any obvious problems on the chip itself, although this was the side I was looking at yesterday, pressing down on. Maybe a couple are a little bit dry, but can't see any obvious problems. But this is what I intend to rework. But just looking around the wider area a little bit, I don't know how well this will come out if I can zoom in on here. There's a couple of fires. Look, there's one there, and there's another one in the area somewhere. I can't see. Yeah, right there, next to that pin there, where there appears to be solder in the wires. So perhaps there has been some work done around here, and that maybe there's something to be looked at. The other couple of things that I noticed was well, obviously there's this U40 chip that we spoke about before. That's this one over here, just to the side of the DMA chip. And you can see this is in a terrible condition, soldering here. I don't think this has anything to do with the DMA chip. I think it's mostly to do with the DSP, which we know has been battered and bruised. But I'll reflow that while I'm at it. One other thing of interest, this oscillator here, U37, this is supposed to be a straight 32 megahertz oscillator feeding the DSP. And on my board, it's a dip 8 size, whereas this is in dip 14. And is actually the PEL frequency, 32.04988, which is the main PEL crystal here on the board, 32.084988. Combined with all the rework done here and the touch on the corner here of the gel, there's definitely been an accelerator fitted to the DSP there, and somebody didn't have the original 32 to put back and put back a PEL one. I suspect that's going to have no effect at all. That's much more likely to be a problem, that one over there. But anyway, I'm going to touch this up. Not going to do the DSP on this particular occasion. Right, so how do I intend to do this? Well, firstly, I'm going to bring in some flux paste, and by some I mean a lot. I'm going to try and work down one side at a time. I'm using my K-tip in a soldering iron for a nice big surface area. And I'm going to start at 290 degrees, which is my normal SMD QFP soldering temperature. However, there's something to bear in mind here. This will almost certainly have been soldered with lead-free solder, given that we're talking 1993. And I'm going to be using leaded solder. So whilst mine will melt quite happily at these temperatures, the original may not, even if I introduce some new solder here. So I may have to wind the temperature up slightly if I don't get much of a flow. So here we go. Let's see how we get on. Okay, so that went quite well, the first pass. Obviously I've got a big blob there. That's fine and somewhat expected. I'd rather have an excess of solder at this point than too little. The whole point is that I'm suspecting a break. So I'm just going to keep winding that down slowly to the end of the row. I can feel the solder melting under the tip. Makes me think maybe I do need to go up a few more degrees. I'm going to take it up to 209. No, in fact, I'm going to go up to 300. Take it up to 300C. So the first pass I do is actually on the legs of the chip to try and make sure that the solder is making contact with the chip. And then I go down the little ridge between the pads and the legs themselves. And that's the bit that I'm getting, that I feel is working less well. Okay, time to wick up that blob. And there should still be sufficient excess solder to make a good contact. That doesn't look too bad. There's still a lot of flux laying around, and we won't be able to tell properly until that's cleaned off. But now the process is basically the same with the other three sides. All four sides have been done there. Need to clean them up and give it a bit of an inspection. But I thought I'd just record the work done here to this where's it gone? U40, there we go, because this is so crusty under that close inspection that I want to get this on camera. It could very well be that U40 has to come off. It looks like there's green under there. Now I don't know what that could be unless the wrong sort of flux is used. I believe plumber's flux, which I have used from time to time to in bulk quantities and to help remove chips. But if you don't clean it all off, I believe that's actually quite corrosive. So I wonder whether something like that has been used on this occasion. Okay. That doesn't look too terrible. Although it really does look like there's something between a couple of those pins. This is the angle I'm looking at, and between pins 2 and 3. See, that's a trace. I wonder if maybe that's just another trace under there. It doesn't seem to have cleaned off. So we need to be a bit careful. We see there's a trace run between those which lost its solder mask. It's definitely had some scrapes and scraps, this one. So I think let's just be a little bit gentle with the amount of solder we put back on here. Otherwise, it has cleaned up quite well. Blue screen, right, that's probably not going to work. Let's flick reset. No. Okay, let's apply some pressure to DMA. No. Right, well, this is looking more like a DFB1 reseating issue, so let's just have another go at that. With the changes I've made to the bus request logic there, I could, or bus grant logic, I could probably actually just put my DFB1X in here, couldn't I? Anyway, let's try again. Reseated and flicking on the output. We're back to that blue screen again. Looks like the Commodore 64. Okay, so the probes are back out. We've got AS here, and we've got our cartridge chip select line there. So let's AS being yellow on here. Let's throw the switch. Okay, we've got ourselves no difference. Well, it's gone green and yellow on the screen, but to no better effect. Okay, that's interesting. So we're seeing a couple of signals. Right, 4. So 4 address strobe activations, and you see that the ROM, the cartridge port chip select line never goes low. 4 address assertions is what the 68030 will do to read on a 16-bit bus basically the initial stack pointer and the reset vector. And so in this particular case, it's obviously getting the wrong reset vector. That comes from ROM. We know ROM was working previously, so I suspect more likely is that actually either the address or data lines here are not properly connected, because we've seen problems with reseating in the past. If this continues and we really don't get anywhere, I'm going to have to solder test points onto the address and data buses, which can do, they are exposed here, and get out the logic analyzer. I was hoping not to do that because that really does make for quite a boring video. Yeah, nothing happening there. So we could check to see whether we have a ROM activation. I think that's one of the vias over here somewhere. Okay, so the memory board's out, so I can reach the ROM chip here. Pin 3 is the chip select. That's 1, 2, that's 3 there, I believe. I think it's one of these vias. Aha. Okay. So level with the top of R210. So, okay, we can put the memory card back in and probe there. With the point of this, of course, being that each of those initial first 4 address strobe activations should be to the ROM. So this signal should go low. Right, let's flick that. No. No. So I think I found something here. This pin here, let me just go through this. That's ground, address strobe, UDS, DTAC, and the one below DTAC there, that is the read-write pin. I've taken DFB1 off just to avoid mixing anything up. And if I test that against ground, we have a short 2 ohm short to ground. That, I think, is why the ROM was not activating, because it thinks the first 4, basically that's pulled low, it should be high for read, so it thinks the first 4 accesses are actually writes, which doesn't decode to ROM, so we don't get our ROM activation. So immediately my thoughts turn to that SDMA chip we reflowed. That's ground. Okay, so I'm touching that to ground, and I'm just counting back. So 36, pin 36, 35, 34, 33 should be read write. There we go. And I'm getting 1.2 ohms there. And none of the adjacent pins. So initially my thoughts are turned to there, but I can't see anything wrong with that. That looks absolutely fine. The address lines, by the way, along there, I've been along there, and they're not shorted to each other. But of course, that's not the only thing we reflowed. We also reflowed this awful looking chip U40 over here. Now this was in terrible condition with a lot of the solder mask missing from the traces running underneath. And guess what? Pin 2 is read write. And if I measure there, my let's bring the multimeter back into shot. Do you remember we had over about, what was it, 2.6 ohms over on the far side of the board? If I go to the ground plane here and pin 2, 1.0 ohms. That's ground, the last pin on the end there. I suspect it's something to do with that reflow that I've done there, and I suspect there's been solder that's run underneath and made contact with a stripped trace, and that has caused our read-write problems, or at least that's my theory. The other line, or the other pin there next to it, pin 1 seems fine. Pin 3, that is also showing 1.3 ohms to ground. That is supposed to be the DSP chip select. So my suspicion is that that would also be failing. Okay, we've still got a hard short to both of those. My concern is that I'm going to toast the board. So I think what I'll do to start with is I'm going to use quite a wide tip on my hot air station here. And we're going to start off with a heat of around 150 degrees. That's clearly not going to melt any solder, but we'll get the airflow up and we'll just warm the region. So let me take you out of it there. So I'm just warming the whole region with a high airflow and a wide tip, just to bring things a little bit up to temperature so that the thermal stress when I actually do concentrate on that chip is a little bit lower. 6-layer board, I really don't want any delamination. Now the problem with using flux paste like this with hot air is that the hot air will blow it away if the airflow is too high, but I'm hoping that, well, I'm going to slow it down when I get to the actual desoldering. Okay, so I think that's, let me just see if I can get my hand in here to pluck the chip. Yep, so I think that's probably enough area warming, so I'm going to turn the airflow right down. And I'm going to turn the heat up to, I'm going to go to 320. And I'm really going to now home in on U40. Try not to do too much damage around it. I'm not too worried about that metal packaged oscillator. The SDMA chip is right next door. That one I'm worried about. The GAL socket I'm pointing slightly away from. The DSP I think is already probably toast, so not that concerned about that. Let's see if we can, there we go. So this is the delightful mess that we find ourselves looking at, and to me that looks very much like a little bit of a solder bridge. Let's get some contact cleaner in there. Mop that up. And yep, sure enough, that looks to me like a massive solder dag. I don't think that's meant to be there, because look, there's the via, and that is leading in completely opposite direction. So I don't think someone's done that deliberately and then resoldered the chip on top. I think that would be a fairly bizarre thing to do. So I'm going to guess that from that excess solder, that has basically run underneath, and perhaps my little bit of rework has caused that, either cause it to flow and just bridge that, or it I can't see that would be my reflow has actually created that dag, but it's obviously made it sufficiently bad. There we go. That it's shorting out. I think that looks rather better, doesn't it? We probably ought to just check for that short. So that to ground. Ground should be this pad here. Correct. And there we go. Open loop. And the same for the chip select pin next to it. Good. And there we go. Proof of the pudding's in the eating. We're back to our blue screen, and I'm not poking the board at all. So fingers crossed that the reflowing there of the DMA chip has helped. Let's press a reset. Give it a quick flick. And resetting IDE, bus error not detected. I think that's normal with my DFB. That's just the way that the expansion port works. And there we go. It didn't detect a keyboard because I don't have one plugged in. I wonder if it will recognise the keyboard now after that reflow. And well, there we go. Still don't have U40 in place, so I do need to reattach that though. as and when. Okay, go on then. Let's try the keyboard. We do get our green light here. Oh, interestingly, actually, my boot up has failed there. Let's try that again. Red screen, resetting IDE, bus out. Okay, initializing keyboard. Ooh, it has. It's recognized the keyboard now. There we go. Look at that. Keyboard revision 2. Well, let's try doing a test then. D. Yeah. And let's do the DRAM test. Oh, this is splendid. Clock seems to be okay. Sorry, it's hunting a bit because I've got like rubber bands and cables and stuff in the way of the screen there. Well, that took a little while, but lovely jubbly. So what else can we do? Timing. Pass, that's good. Don't have any audio. Short blit. Oh, now this will be interesting because I have basically hardwired the bus grant. So this could hang, or, well, if it works, brilliant. I'd be surprised if it works. That should go green pretty much straight away. So yeah, I think my hard wiring of the bus arbitration is not going to cut the mustard. Okay, that needs a little bit of attention. So effectively we're running in a sort of single or non-bus arbitration mode. Analog audio, timing, yeah. Can't really do any of these things. OS ROM. Yep, okay, happy with the ROM. And that is the ROM that came with the board. So that's nice. Audio video keyboard. I don't have an IDE. No, there's not much more. Real-time clock, I suppose. L. Testing RTC. Failed. Well, that could just be battery's dead, or it could very well be that there was some terrible soldering going on around there. That could actually just be a genuine fault. Right, so hidden over there behind this HDMI wire that's being strewn across the proceedings, that is our VGA monitor, and that is now attached to the board under test. I'm throwing the switch, I'm seeing activity, and it's gone green. There we go. Okay. No, so it's capable of detecting the VGA monitor. Let's do an auto adjust. There we go. So what if we try that video test now? VGA test number 4. Well, it doesn't look centered again. Let's do another auto adjust. There we go. Very nice. Well, I'm rather happy with that. Well, there we go. I think this is as good a place to leave it for part 2. You can see DFP1 is toggling away there happily. We've got the clock going there. The bus grant has occurred, and the address strobe line is running nicely. You can actually see that over there on the scope as well. That's the cartridge chip select there in blue, and the AS line is just behind it in yellow. All running fine. You can't see just over on the screen there. It's performing the RAM tests on a loop at the minute, just for a stability test, and obviously even the keyboard is working now. So the reflowing of the SDMA chip, I think we did it. Sorry, it's all hidden under there because the keyboard cable is very short. I have yet to replace that U40 chip. That does need to go back on, and that will be probably the first thing we do in part 3. But for the time being, I am very, very happy. Items that we still need to address. Clearly, bus arbitration is not quite working. I don't think we could boot we certainly couldn't boot the OS with the broken DSP anyway. But I don't think we could get very far without bus arbitration, because the DMA chip simply can't talk to anything. Blitter won't work. floppy drive won't work. IDE could work, but I think it shouldn't be too complicated to get that sorted out once we're happy about the reliability of everything else. I'm incredibly pleased. This board is, I would say now, 80% of the way to being a fully functional Falcon. And that is simply delightful from the place where we started. I'm really pleased. And I look forward to seeing you in part 3. Many thanks for watching. Catch you next time.